So I want to start by both setting a context for how we think about the concept of similarity, and then also getting to a result that we're going to use in a variety of different ways when it comes to proving similarity criteria for triangles. I want to start with the midline theorem that we saw in our previous chapter. The midline theorem said that in a triangle ABC, if I label the midpoints of the sides AB and AC, if I call them D and E, and I connect D and E with what we call a midline, then two things are true. First of all, we know that DE is parallel to BC. That's the first result of the midline theorem. And the second is a result that compares the lengths of DE and BC, that says that the length of DE is half the length of BC. So let's think more broadly about this theorem for a moment and ask, why is it plausible? Why do we think that this theorem was really a true statement? What's really going on here? Well, if DE is really half the length of BC, let's focus in on that number, 1/2. We can isolate that number in the equation by just dividing both sides by BC. And we can state this equivalently as the ratio of DE to BC is 1/2. So my question is, where else in this figure does the number 1/2 show up? What else are we actually having? And the answer lies in the word midpoint. After all, to construct this midline DE, we began by cutting the side AB in half, so that AD is 1/2 the length of AB. And likewise, we cut the side AC in half, so that AD over AB is also 1/2, and AE over AC is 1/2. So there's a lot of halving going on in this figure. We've halved the side AB to construct the midpoint D. We've halved the side AC to construct the midpoint E. So maybe it's no surprise then that if I have two sides of a triangle, I also end up halving the remaining side. But that turns out not to quite be strong enough. We need one more observation to close this loop. When we go from the big triangle ABC in this figure to the smaller but embedded triangle ADE, we've halved the side on the left AB when we made it into AD. We've also cut in half the side AC to make AE. But there's another thing that we've also done. We've maintained the angle measures in this triangle. It's because after all, the angle at A here is common to both triangles. And if we believe point 1 of the midline theorem, that DE is parallel to BC, then we have all of those important parallel line and transversal theorems that will guarantee for us that the alternating angles are also congruent, so that the angle at B is congruent to the angle at D, and the angle at C is congruent to the angle at E. So in the process of having two sides of this triangle, we've also maintained all of the measures of the angles in these two triangles. And so from that standpoint, maybe it's not surprising that the net result of this is we end up cutting the third side in half as well, so that when we go from the big triangle ABC to the smaller triangle ADE, because we've cut in half the length of two of those sides, we also cut in half the length of the third side, so that DE is half the length of BC. So the midline theorem makes some intuitive sense, because all we're really doing is cutting this entire triangle in half in some way. So can we generalize that? What would happen if I take this line at DE, which we constructed by insisting that it connect the midpoints of the two sides AB and AC. And what if I decide to relocate that line so that maybe it's here instead, or maybe there, or here, right? What if I move that line up or down in such a way that I'm still maintaining its parallelism to BC, because we're going to need that parallelism to make our conclusion here, but we're not necessarily cutting the side in half. We're cutting them in different proportions than we used to before. Can we generalize the midline theorem? So here's a conjecture. Let's suppose I choose points D and E on the sides AB and AC in such a way that DE is still parallel to BC. Now, we would conjecture, we'd like to say, that whatever ratio exists between AD and AB, for instance, by however much I've cut the side AB down, by whatever ratio AD stands into AB, that's the same ratio as we get on this side, the ratio of AE to AC. So whatever ratio I've cut one side down, I've also cut the other side down by. And that, as a consequence, that same ratio also exists for the remaining pair of sides. So that's what we'd like to be able to say. That's our conjecture, that even if we're not cutting the sides in half as we were in the midline theorem, that those ratios are still preserved as long as my line here is parallel to the side BC. So in this example, I've sketched it as though D and E are cutting the sides AB and AC into ratios of 3 to 1. In other words, whatever the length BD is, the length AD is 3 times as long. And ditto for CE compared to EA. It's 3 times as long. What we would say in that case is that we've cut each of these sides into, when we move again from the bigger triangle ABC down to the smaller triangle ADE, we end up with sides which are only 3/4 as long. So AD is 3/4 the length of AB, and AE is 3/4 the length of AC. And so that ratio, 3/4, we can describe as having the two sides of triangle ADE are 3/4 as long as their corresponding sides in ABC. And so we'd like to be able to conclude that that remaining side, DE, in the smaller triangle, is also 3/4 the length of BC in the bigger triangle. Is that the case? Are we guaranteed that that ratio will remain if DE is parallel to BC? And it turns out that the answer is yes. This is one of the things that we'll prove in this chapter, and we end up using this result actually quite a bit in discovering the similarity criteria for triangles in studying similar figures in geometry.